Hello, Year 12s or Year 13s, depending on your outlook, I guess. Mr. Rendell here, and I am putting together a series of vodcasts for What's in a Medicine module. So the 10 lessons for What's in a Medicine will be flip taught. And what that means is I'm going to be producing a vodcast type episode for every lesson, which you're supposed to watch before the lesson. It will contain basically the specification points for that lesson in terms of the content and questions that I ask in it. So hopefully by the end of the podcast, you'll have a good understanding of most, if not all, of the specification points for each individual lesson before you actually go to class. What that means is hopefully that you can use the time in class to then do practice questions, peer assessment, spend more time on practicals and exam questions, and generally just asking your teacher any extra information and checking that you do understand it fully. Now, it's the way that I'm going to do it is that I'm going to have questions at the start that hopefully by the end you can answer. If you can answer those, then that's excellent. If not, you might need to go back and just double check through a few things or use your textbook, the ideas book, or it may be that you just need to write down some questions to take to your lesson to ask your teacher for them to clarify anything you didn't understand. Now, there will be questions throughout this. Of course, you can pause, you can rewind, so all of that kind of stuff. It would be good for you to make notes on these because you then have reference and things to take to your class to then modify or to add to. And there will be questions in sort of blue boxes in this. So you can pause it there, attempt those questions, and then of course I'll go through them and hopefully you can check and see what you got right, what you got wrong. So that's kind of the way it's going to be done. Flip teaching because you're going to be kind of doing the learning yourself, and then in the class we're going to be sort of facilitating the extra learning that's needed, or the clarification or the application of that knowledge into new circumstances. So checking whether you do really understand a concept by applying it to something new and unfamiliar, like an exam question, and hopefully that will actually cause you to have more of an understanding of each of the different concepts and ideas. It also means that hopefully you'll have more time to do the practicals in class. We can go through more of the theory and things in these so that you can get a better idea of why you're doing the practicals, and then hopefully when you arrive there you'll have a good understanding of what you're doing and why. So yeah, I won't talk anymore, so let's just get on with it. Now, they're the kind of questions that would be good for you to be able to answer by the end. I'm not going to read them out because of course you can read and you can pause this. So let's get going. Carbonyls then. So you've met carbonyls before because you've met aldehydes and ketones. You've looked at it in terms of oxidizing alcohols. So you've looked at oxidizing, primary and secondary alcohols to form either aldehydes or ketones. And we've got their general structure there. So a carbonyl group is found in the middle of a chain with two different R groups or two of the same R groups either side. And a carbonyl got this one R group. An aldehyde got this one R group and the carbonyl group on the end. So it has this hydrogen, and it's this hydrogen which changes the chemistry of between these two mainly, at least for what we're going to be looking at. Now, there will be some sort of yellow boxes throughout which aren't directly linked to the specification points and what we're going to be covering in class, but if you want to find out anything extra or just check whether you can do something before I explain it, then you're free to do so. So, name the following carbonyl compounds. So in a blue box, that means it's a question. So what I'd like you to do is just copy these out and then see if you can name them and be as diligent as you can. So think about all the different rules and think about all the different things. Make sure I'm not tricking you by drawing things in a strange way, and see what you get. So pause it now, give it a go, and then unpause it and I'll go through the answers. Okay, hopefully you've given it a shot, and we will go through those now. So first one, 2-methyl pentanthreone. So it didn't matter which side you started counting here. You could have started counting from this side or this side because the carbonyl group is actually same distance from both sides. So you could have gone 1, 2, 3, 4, or 1, 2. Now I went 1, 2 methyl because it's gives it a smaller number, just looks a bit neater. So 1, 2 methyl pentanthreone. Since it's 5 carbons long, 1, 2, 3, 4, 5, and this is on the third carbon. Okay, next one. 3,6-dimethyl octan 4-one. So here I was kind of trying to throw you a little bit by putting this group pointed upwards like this. Now, you'll actually notice that if you count 1, 2, 3, 4, 5, 6, 7, 8, it's actually 8 carbons long, the longest chain. So this is the side group, or both of these are side groups as opposed to this one like this, even though I've drawn it to make it look like it is a side group. If you were to sort of twist it round, this would be pointed up, this would be a straight chain. So yeah, let's count. So we've got to count from this side since the carbonyl group is closer to this end than this end. So 1, 2, 3. 4, 5, 6. So 3, 6 is the dimethyl part. We know it's octane because we counted 8, and the carbonyl group is on the fourth carbon from here. 1, 2, 3, 4. So 3, 6 dimethyl, octan 4-one. Next one's quite easy. 2-methyl propanal. So 1, 2 is on the second carbon, and then 1, 2, 3. So propanal. Last one. 4-ethyl, 2-methyl hexanal. Now, you may have got it the other way around. You may have put 2-methyl, 4-ethyl. Does that matter if you got it around that way? Well, yes, it does, because in this sense, the groups must always, the prefixes, must always be in alphabetical order. So 1, 2, 3, 4-ethyl. So even though we've reached the methyl group before in our compound, when we write it down, we put the ethyl group first because it's higher up in the alphabet. So 1, 2, 3, 4-ethyl, 1, 2-methyl, hexanal because 1, 2, 3, 4, 5, 6 long. Okay, and we know it's a aldehyde because we have this hydrogen here. Okay, so that's the naming out of the way. Hopefully you got all those right. If not, then hopefully you can see where you went wrong, and you can maybe practice a few more of those in lesson. Now, this is a bit of recap. So forming aldehydes and ketones, we know that we form them, we make them from our alcohols. We oxidize alcohols, primary or secondary alcohols, to form either aldehydes or ketones. So here I have 3 alcohols, propan 1-ol, octan 3-ol, and 2-methyl pentan 2-ol. And what I would like you to do is, first of all, decide what reagents and conditions are required to oxidize these alcohols, and secondly, what products would be formed in each of these 3 cases. So, bit of recap on oxidation of alcohols, see if you can find the reagents and conditions, and work out what the products would be. Of course, pause it and then start it up again when you're ready. Okay, so reagents and conditions first of all. If it's going to come up, there it is. Acidified dichromate under reflux. Okay, so you could use potassium dichromate and have it heated under reflux. So we don't want any of those volatile gases leaving. We want it to condense in our Libby condenser and drip back down into the reaction flask and just keep going. So under reflux, acidified dichromate, we acidify it with sulfuric acid, can be used, and that's what we're going to need in all of these 3 cases: acidified dichromate and do it under reflux. So the first one, propanal, okay, because it's a primary alcohol, which means that the OH group will get oxidized to form a C double bond O, but we'll still have that hydrogen attached to that carbon on the carbonyl. So we'll get propanal, which is our aldehyde. Octan 3-ol is a secondary alcohol, which means that we'll form octan 3-one, which is our ketone. And finally, 2-methyl pentan 2-ol, hopefully you would have realized if you'd drawn it out that there'll be no reaction, because this is a tertiary alcohol, which means that there are no hydrogens attached to the carbon, which is bonded to the OH. So there's no way that it can be oxidized. So hopefully you got that right. Now, hopefully you noticed that propanal being formed here would only be formed if we managed to distill off the aldehyde as it was made. If we leave it refluxing, it will actually oxidize further to the carboxylic acid, which we'll look at in a bit. For now, though, we're just going to have a quick look at the tests for an aldehyde or a ketone. So if you had 2 colorless liquids, you weren't sure if one was an aldehyde or if one was a ketone, this is the test that you could perform to check that. I'm going to show you just a quick demonstration of the reaction, and you'll be able to see a positive result for the aldehyde and see what a negative result looks like, indicating a ketone. Okay, so what's happening here is we've got 2 boiling tubes filled with Felling solution, which is this dark blue liquid here. Felling solution is essentially just copper 2 plus ions and an alkali. So the copper 2 plus ions are complexed with some ligands, and it gives it that dark blue color there. So that's essentially what it is in both cases. All you really need to know is that it's copper 2 plus ions and an alkali. It comes in two parts, the alkali part and the copper part, so two separate solutions which you mix to form this dark blue liquid here, since it does deteriorate over time. So you just make it just before you want to use it. Now, what we're going to be doing is adding our aldehyde to one, ketone to the other. They're identical, otherwise there's just same amount of filling solution in each, and we're just going to see any differences that occur here. So it's done in a water bath at about 60 degrees to ensure that it's hot enough for the reaction to take place quickly, and we're just going to add our aldehyde and ketone to both, give them a mix, and leave them just for a bit to see anything that might happen. Now, the aldehyde, since it contains that hydrogen on there, on that carbon-carbon, can actually act as a strong reducing agent using that hydrogen. And it can actually reduce copper 2 plus to copper 1 plus, which gives us a nice red precipitate as a new compound is formed. Whereas the ketone, which lacks that hydrogen, cannot actually reduce the copper 2 to copper 1. So nothing actually happens there. Now, the reaction's been going for about 5 to 10 minutes, and you can already see the difference in the two solutions. Now the ketone solution is just the same as it was before, no change, whereas the aldehyde solution is very much still reacting and very different to when it was before. You can see that dark red precipitate there. Now that is the copper oxide, the copper 1 oxide, so that's Cu2O, and that is the compound that's formed when the aldehyde, in this case methanal, reduced the copper 2. Now, some of that might actually be pure copper in there, since methanal is such a powerful reducing agent, it can actually reduce the copper 2 ions all the way to copper metal. So there's a chance that some of that is actually pure copper. Okay, so hopefully that demonstration was clear enough and you've got a good understanding about that test now. We're going to have a look at the reactions of the carbonyls, and we're going to start off with oxidizing. So we can only actually oxidize a aldehyde. Okay, we can't oxidize a ketone any further than it has already been oxidized. Since we used, if we have a secondary alcohol, we can oxidize it to a ketone, but no further. Whereas with an aldehyde, we start with a primary alcohol, we can oxidize it to an aldehyde, and then if we carry on refluxing, then we can actually get a carboxylic acid. So if we did, distill off our aldehyde, but then we wanted to oxidize it further to get our carboxylic acid, we just use acidified dichromate under reflux again to do that, to get our carboxylic acid. So the opposite then of oxidizing. So we have reducing the carbonyl group. Now, my question to you is it possible for us to go back to an alcohol from an aldehyde or a ketone? So in this case here, we have a aldehyde going back into a primary alcohol, and over here we have a ketone going back into a secondary alcohol. We know that tertiary alcohols do not oxidize anyway, so of course we're not going to have any, there's no tertiary carbonyl that we can have there. It's just the aldehyde or the ketone. Now what I would like you to do is, using your data sheets, hopefully you've got them, find the reagents and conditions for this reaction to take place. It's not one that you are expected to memorize, which means that it is on the data sheet, so it's useful for you to know that it's there and just to see what it is. Okay, so hopefully you found that relatively quickly, and you'll see that very simply all it is NaBH4, okay, which is sodium tetrahydridoborate. Okay, now that is just a reagent, a very, very, very strong reducing agent that is used to actually reduce our carbonyl group, so either our aldehyde or our ketone, back to an alcohol, and we need this very strong reducing agent, sodium tetrahydridoborate. Excellent. Right, next reaction then, nucleophilic addition. Okay, so this is where it's not just reagents and conditions we need to know, it's now a mechanism that we need to know. And in this case, it is a nucleophilic addition. So it's going to be involving something, and it's going to be involving something else. What those somethings are, I'm going to leave for you to work out. So have a think. What are those two things going to be? Okay, so hopefully you would have realized that you need a nucleophile. Okay, so that's a nucleophilic part. In this case, it's going to be a cyanide ion. Okay, so a cyanide ion. And also for addition, we must have a double bond for this cyanide ion to add across. Yeah, in electrophilic addition, we had carbon-carbon double bond, but in this case, since we're doing aldehydes and ketones, we have a C double bond O, a carbonyl double bond there. So that's what we need for this to actually take place. Now, what I'm going to do is I'm going to let you see if you can work it out, first of all. So using methanol and cyanide ions, okay, see if you can work out what the mechanism might be, knowing that it's nucleophilic addition, okay, and also knowing that the reaction is done in the presence of water. So you can use hydrogen ions if you need them, because they are there if you need to use them. And the cyanide ion looks just like this. There's one thing missing, of course. It's got a negative sign on the carbon, which means that the lone pair of electrons are located on this carbon. So you'll need to make sure you include those when you draw your mechanism, since it's very important to show those. I'll give you a chance to give it a go, and then I will show you how it's done. Okay, so we're going to have a look at the nucleophilic addition mechanism, and we're going to be doing it for aldehydes and ketones. So the nucleophile we're going to be using is a cyanide ion, as you can see here, and the other species will be either an aldehyde, which is this, or a ketone. We can easily convert this into a ketone by adding another R group there, but the mechanism will be the same for both. Okay, so it doesn't really matter what this group is here or what this group is here. Obviously it does for the product, but the actual mechanism itself will run exactly the same, no matter if it's a ketone, as shown, or an aldehyde like this. Be the same. So we'll run with it just being an aldehyde for now, but like I said, there's no difference there. So first step for us is to really look at the aldehyde and look for partial charges. So we can see this carbon is actually bonded to a very electronegative atom, e.g. the oxygen, which allows us to put in these partial charges here. And that shows us that there's an area for these electrons here to attack. Okay, so always with curly arrow mechanisms, always show the curly arrows moving from the electrons themselves. Okay, so make sure you draw them in if they're not there. If you haven't drawn them in, if you forget them off and you just do the negative sign, add them in just to show that it's those pair of electrons that are forming that bond. Since carbon can only make 4 bonds, it can't stay like this for long. So this bond actually here will break, so that double bond will partially break, and 2 electrons will move onto the oxygen there, giving it a negative charge. So that was our first step. Let's have a look what was made. Okay, so that's what should be there then. Negative charge moved onto the oxygen. It's quite stable like that, but it will react relatively quickly with any hydrogen around. So any hydrogen ions will be picked up very, very quickly by this oxygen here. So since we're doing this in water, you don't want to be using hydrogen cyanide as your source of cyanide ions, since hydrogen cyanide is a very toxic gas. So actually what's usually done is potassium cyanide or sodium cyanide is dissolved in water with a little bit of sulfuric acid added to drop the pH down to about 4 or 5 and to supply some more of those hydrogen ions there. So you'll usually have H3, H3O plus around, so ions of that nature around, which is a source of hydrogen ions for this oxygen to pick up. So we can put H2O here and we can draw our final product, which will just be exactly the same as the one before, but that oxygen has now picked up a hydrogen. So we have got our hydroxy group here, okay, and a nitrile group here. So the generic name for these products, when you perform this nucleophilic addition on a aldehyde or ketone, will be a hydroxy nitrile. Okay, so that would be hydroxy nitrile. Yeah, and that you don't need to know about naming them specifically, but as a general, generally, the hydroxy nitrile makes it a hydroxy nitrile. Okay, so hopefully you had a go at that, or you saw how to do it and have got a good understanding of what's actually happening there. If not, of course, watch it again if you need to, or write down any questions that you need to bring to class. Just showing you here a general hydroxynitrile again, just saying that this is the parts that are important. Yeah, the R groups are not important. The cyanide, the nitrile group here, and the hydroxy. So we call this a hydroxynitrile, but you don't need to know any more than that. You don't need to worry about naming them if these are, methyl groups. All you need to know is that a hydroxynitrile is the product. So hopefully that was useful for you. Just if you need to double check anything, do so. You can use your textbooks, you can, search on the internet, whatever you need to do, and see if you can answer these questions. So, what are the key reactions of aldehydes and ketones? What is the test for determining an aldehyde or ketone? And what's the Curly arrow mechanism for a nucleophilic addition of cyanide ions across a C-double-O bond? So, check that you know those, and then in a second I will show you sort of the answers for those, and hopefully you are happy with that. So, oxidation reduction and nucleophilic addition, they're the reactions that you should be familiar with. The test is using Fehling solution. You can use Benedict solution as well, which is essentially the same thing. It's just a source of copper ions and an alkali, but Fehling solution is fine, just to memorize that one. And the aldehyde forms a red precipitate, and the ketone has no reaction. So that's the kind of result there. And finally, with the curly arrow mechanism, make sure you've got partial charges, curly arrows starting and ending in the correct place. So, from electrons and ending at a positive charge, and make sure that your hydroxynitrile is the thing that's formed. Okay, so cheers for listening and good luck.